Hello and welcome. Today I'm going to take you on a journey through the evolution of our universe. This video is based on the Big Bang Theory, and even though there are other theories of the universe, the Big Bang is the most famous. But more importantly, most of the proof that we have found is steering towards it. I do also recommend that you check out two particular videos of mine, since they will help you understand this one a lot better. The first one is the standard model of particle physics. This one is actually the more important one because this will help you understand the different particles and the different forces formed during the different time periods of the Big Bang. The second one is quantum fluctuations, and this is also quite important because this will help you understand how the Big Bang really occurred. So without any further ado, let's get started. So where did the Big Bang Theory come from? Who even thought of it? It was in 1927 when a Belgian Catholic priest by the name of Georges Lemaitre proposed an ever-expanding universe. He did this by simply observing galaxies, and he saw that most of the galaxies in our universe were moving away from us. Well, how did he know they were moving away? Because he saw that the light from the galaxies was stretched, and therefore it looked red, or the longer wavelength of light. This is also known as the redshift of light. It was in 1929 when the famous physicist Edwin Hubble confirmed Lemaitre's observations. But where did the term Big Bang Theory come from? That was all the way in 1949 when an astrophysicist by the name of Fred Hoyle coined the term. It's actually quite ironic because Fred Hoyle was completely against the Big Bang Theory and never believed in it, and that is because he was one of the researchers of another theory of the universe, the steady state theory. So now let's actually get into the good stuff. Let's get into the evolution of our universe. It was 13.9 billion years ago that the universe began, and it began with a single point. Everything we know today, or the energy of everything we know today, the Earth, the solar system, the stars, the galaxies, the entire universe was concentrated in this one point. And this point is what we call an initial singularity. Initial because it initialized the Big Bang, and singularity because a singularity is an infinitely dense, or a lot of stuff packed into it, infinitely small point. And this is what began the Big Bang. A very common question asked over here is, well, where did the singularity come from? And the most popular theory to answer that question is the multiverse theory, which suggests that we are not the only universe, but there are various others. And that states that either on two universes colliding with one another, or one universe collapsing, it created our universe. But when we ask the question, where did the first singularity come from? I don't really know. And that's not because I haven't done enough research, but because we don't know the answer. Forget a theory, we don't even have an idea of where the first initial singularity came from. And to me, that's actually quite scary. To think of the most fundamental question in the universe, where does everything come from, has no answer. It's quite scary. So let's stop focusing on the stuff that we don't know and let's start on what we do. So what do we know? Well, we do know how the singularity expanded into the universe we know today. Or at least, once again, we have a theory. So how did this happen? This happened because of a quantum mechanical phenomenon known as quantum fluctuations. And this is where that video comes into play. Quantum fluctuations is a phenomenon when two particles can randomly pop in and out of existence. Right now, currently, around me, there are thousands of particles popping in and out of existence. And how do they do this? Well, instantaneously, when they pop into existence, they take some energy away from the system. In this case, the system being the singularity. And remember, energy can't really be created or destroyed. It has to be taken from somewhere and given back. So to give back the energy, both of these particles collide into one another to give it back. And this rapid energy fluctuation, you can say, of the particles taking in, giving back, caused the singularity to expand into what we know today, the observable universe. However, that's not quite the end of the video, because the Big Bang has a lot of information. From the beginning all the way to what we know today, there are a lot of separate time periods or epochs where different things happened. And each epoch is responsible for some stage of the universe. So let's get into these epochs. The first epoch is known as the Planck Epoch, named after the very famous physicist Max Planck. And it's named after him because this occurs in a time period known as Planck time. The value of Planck time is 5.39 into 10 to the negative 44 seconds. Now, even though it is a very small time period, it is when the universe became from a point to an expanding universe. Now, during the Planck epoch, all the four fundamental forces of nature, the strong nuclear force, the weak nuclear force, the gravitational force, and the electromagnetic force, were one fundamental force. To learn more about all these forces, once again, the standard model of particle physics has everything explained. Now, to actually describe the universe's state during the Planck epoch, once again, we have a few theories. The most popular ones being the ekpyrotic universe theory, or the Hartle-Hawking state, named after two very famous physicists, John Hartle and Stephen Hawking. Now, I don't want to go too deep into these theories because it does take a little bit away from what we're talking about, but I do recommend you definitely check up and read up on them because they're really interesting to read upon. So what happens after this? After the Planck epoch, what then? Does the universe just continue to expand forever and magically become what we know today? Well, obviously not. After the Planck epoch comes another very important one, the Grand Unification Epoch, after the Grand Unification Theory. And this happened between 10 to the negative 44 and 10 to the negative 36 seconds of the Big Bang. This is also a very important epoch, because in this epoch, the four fundamental forces split up into two separate ones, the gravitational and the electrostrong, where the electrostrong force is the electromagnetic, strong, and weak all combined. Now, at the end of the Grand Unification Epoch, the electrostrong force also separated into two separate forces, the strong nuclear force and the electro-weak force. Now, this separation caused the next epoch, the Inflationary Epoch. And this is actually my personal favorite because in this one, something really amazing happens. From 10 to the negative 36 to 10 to the negative 32 seconds of the Big Bang, something really crazy happens. The universe expands from its original size to 10 to the 78 times its original size. This, to me, is just crazy. And ladies and gentlemen, another interesting fact, this expansion was faster than the speed of light. However, it does not break Einstein's special theory of relativity, where he states nothing can travel faster than the speed of light. Because what he actually states is that no information can travel faster than the speed of light. And the space-time continuum, or space, is not really any information. It's just space that is expanding. Now today, really weird, the universe is actually accelerating in its expansion. Even though the initial stages of the Big Bang presume that the universe should be slowing down, it's apparently sped up. And I'm going to talk a little more about that a little later in the video. But for now, let's just continue. So what happens after the Inflationary Epoch? The most noticeable thing? Quarks finally form. Quarks, the most fundamental particles in the universe, at least till what we know today, were formed. And they are responsible for making up protons and neutrons, two very important particles in the universe for most things to exist. A very common question that people ask over here is, well, if quarks were formed, wouldn't antiquarks also be formed in equal amounts? Antiquarks, or antimatter in general, is the exact same thing as matter, except for its charge. The mass, the size, everything stays the same except for the charge. For example, an electron, which is negatively charged, has an antimatter particle called a positron, which is positively charged. Now this is where things start to get weird. Why wasn't antimatter created in equal amounts as regular matter? As we can see in the universe today, ordinary matter clearly is more than antimatter. But why does this happen? This is actually another question that we don't have an answer to. And this phenomenon that antimatter has not been created in equal amounts as ordinary matter is known as baryon asymmetry. So actually, one thing I forgot to mention is that just before the quarks were formed, the Higgs field was formed. I also do have a dedicated video on the Higgs boson and the Higgs field, and the fact that the Higgs field is what creates mass. When we ask ourselves, how does this proton have any mass? Where does the mass come from? It comes from the quarks. Where does the quark's mass come from? And that is from the Higgs field. So what happens after the quarks? This is where something really interesting happens. Primordial black holes. Primordial black holes are theoretical black holes that formed just in the initial stages of the Big Bang, simply a few seconds after. Till today, we have been searching for primordial black holes, but we haven't found anything concrete. After these stages, then we have the lepton epoch, where leptons are created, or the other fundamental particles like electrons, for example, are created during this time period. And then we have nuclear fusion, when the first nuclear fusion starts. Protons and neutrons collide with one another. And this is what sparks up nuclear fusion. Now, however, even though you may think, oh, nuclear fusion, therefore stars may form, stars didn't form after 400 million years after the Big Bang. So what happened for these 400 million years? These years were known as the Dark Ages. And the Dark Ages technically stopped after 1 billion years after the Big Bang. What the Dark Ages represented is an era where there wasn't enough light to light up the universe, because stars hadn't completely formed yet. Also during this time period, the cosmic microwave background, or the CMB, was formed. And this is what we can observe today. And this is one of the leading proofs of the Big Bang. 1 billion years after the Big Bang is really when we can say the universe started to look a little like what we know today. So let me answer another question for you that I have proposed in this video. Why and how is the universe accelerating in its expansion today? As we can see, after the inflationary epoch, the universe started to slow down in its expansion. But if we view the universe today, we see that it is expanding, and it's accelerating in its expansion. And this is what confuses many people, even many physicists, because we really don't know what's happening. But once again, we have a theory. This theory is dark energy. Dark energy is what is dominating the universe today. It takes up about 70% of the known universe, while the rest is dark matter, and just a mere 5% is ordinary matter. So think about this. The Earth, the stars, the entire galaxies makes up only 5% of the universe. So now think about the sheer amount of dark energy. And do you want to know what's even scarier? Well, I'm going to tell you anyways. The fact that we have no idea what dark energy consists of. We have a few theories, but absolutely nothing concrete. We're not even trying to look for dark energy. One thing we are trying to look for is dark matter. But that is another state, and I'm not going to get into that right now. But dark energy is what theoretically is forcing the universe to accelerate in its expansion. There are some theories that propose that dark energy is not really expanding the universe, but just more dark energy is being created, and therefore the universe looks like it's expanding. Now there are many theories, and I could create a whole dedicated video on dark energy, but in essence, there's a lot of it. I really do hope that you enjoyed this video. It was a lot of fun to make it. And until next time, stay sharp.